All right. Hey, how's everyone doing? Um, we're winding our way down here, and we're just going to look at parts of Chapter 8, and we're going to look at the idea of. I'm going to make sure this is recording. Give me a second here. Make sure quarter marking here. Make sure the marking shows up. Because sometimes when I start these videos, it doesn't have the windows right. Looking good. All right, we're looking good. I'm feeling good. All right, come back here. And what we're going to do is we're going to look at a hypothesis with two samples. And we're looking at the first part of chapter 8. And this really leads into some ideas that can be used for when we're designing an experiment. And in these two samples, well, sample 1 and sample 2, we can look to see if the samples are independent or dependent. So in an independent sample, or independent samples, I guess I'll use the plural, there's two of them. So there's some space, some data I've collected, and some other data I have collected. And there is a difference between them. And if they're independent, any of the samples from here, x1, x2, x3, and any of the samples from here, and I'll say y1, y2, y3, these individual things, they're not related. So x's are not related to y's. Now, if they're dependent, mathematically they might look slightly similar, but there's some reason that each member has a corresponding member over here. And that correspondence means that this piece of data matches exactly with this piece of data. And this matches with this, and this matches with this. And so that would be dependent samples. There's some relationship with dependent samples. And that doesn't mean that I have the first one over here and I have the first one over here. When this data is taken, it's taken in pairs. And there is some characteristic that relates these two things across from each other. And so for an example, if we have a sample number 1, and in it we have triglyceride levels of 70 patients, and sample 2 is the same 70 patients after a treatment. Patients, I'm just abbreviating here, after treatment. And so we have the triglyceride levels and we apply some treatment to them. Well, we're going to say this is dependent. Because in sample 1, right, the first patient, they have a measurement in sample 2, in sample 2 as being the first patient. So we could say sample 1 are my x's and sample 2 are my y's. And so the first patient corresponds to the first patient after treatment. And the same happens here. And the idea that you're going for is, patient 1 might be male and in the mid-30s, where patient 2 might be female and 20s. And these factors that are the same between each, the only thing that's different is the treatment. Now, if you were looking at the effect of the treatment in general, these differences could add up. They could influence the parameters. But the parameters between this sample and between this sample, the only difference is that treatment that's been applied. And so dependent samples are a way of gathering things that we may know or we don't know in our experiment and making sure that all the same things match. And it's a good way to control what we're looking at, because the only thing that's different between x2 and y2 is the treatment. So let's look at the opposite then. Let's look at what we have when they're independent. And so let's say sample 1 is the score for 38 adult males on a psychological screening test. And sample 2 is the score for 50 adult females of a psychological screening test. And these are independent samples. There is nothing that relates any measure in sample X, which I'll say will be the males, X, or sample Y, which are the female. In fact, I can't even match one item for each. There's only 38 X's in here, right? All the way to X sub 38, while the Y's go all the way up to 50. And so I can't do a pairing between this, or there is no paired data. And so this is what independent samples look like. And what we need to do is, when we now talk about working with samples, though, we can use a very similar technique between two samples. We're going to use a null hypothesis that compare the two samples. And so the null hypothesis we're going to look at, and we're going to talk about how these two populations, or the parameters between the two populations, compare. And we get the same idea. We get our null hypothesis is going to be that the means between sample 1 and sample 2 are the same. And so the alternative would be that the means are not the same. All right, that was our one case. The other case we had was that the null hypothesis, these should be definitions, not equal signs. And the other case we had was my null hypothesis was of the first sample is less than and equal to the second sample, which means its alternative is that the first sample is greater than the second sample. And the third case that I have is that my null hypothesis was greater than or equal to of sample 1 was greater than or equal to sample 2, which means the alternative, sample 1, is less than sample 2. So notice how we're comparing sample 1 to sample 2. Previously we had said, the null hypothesis is equal to some value or less than some value. Here we're taking one sample and we're comparing it to another with our hypothesis test. In all cases, when we run the test, we run under the assumption that the two sample means are the same, that the means for the sample are the same. And so what we want to end up doing is what we want to focus on then is the difference of means is what the test becomes. And what I want to do here is this is the first little video. It talks about how we classify if two samples are independent or dependent. The next little video I want to put up, we're going to do a test to talk about the difference between the mean in sample 1 and the mean in sample 2.